Yeah, hello Kirtana, I'm audible.
Yes, sir.
Okay, fine. Just a second. Just switch. Okay, I'm just sharing my screen now. Please look at that. Yeah, I think it's visible now. Okay, we are going to extend the session with whatever we have left in the last class. Okay, so what was the last topic we discussed, Kirtana? Yeah, Kirtana. So in the last class, I think yeah, look. In the last class, we were discussing about what's the work done to rotate a current carrying loop, right? Okay, so therefore, are you clear with the concept? Uh,
Yes,
some problems also we did in the last class, right? So look,
yes,
let's start with moving coil galvanometer. Okay, I'll be teaching now moving coil galvanometer. The discussion of this galvanometer was I also discussed about this galvanometer in the maybe current electricity chapter, but we didn't discuss the what I can say construction of this. Okay, we only discuss about the use case. What is the use of it? Okay? Here we are going to discuss how it actually works. Okay, so, so basically, okay. Okay, so how this is going to make, okay? So basically, paper for this, we are going to use a radial shaped bar magnet. Okay. Uh, Before this, assume this is a coil. This is a coil. This is a coil. Okay. Assume the area is A. Area is A. There's a current flowing in it. This is current flowing in it like this. Right? So, Kirtana, if I ask you what is the direction of magnetic dipole moment, you can simply say, sir, the dipole moment is nothing but area vector and multiplied with the current vector. So you know this not current vector. Actually, magnetic. What is the magnetic dipole? That is nothing but B cross A, right? B cross A. So that gives you the magnetic dipole moment. So what is the direction of that? You can simply say whatever the direction of magnetic field is that. Generally, we take that as a direction of magnetic field. So here, this is going to be the direction of magnetic dipole in this particular case. Okay? Uh, let's keep I also. Yeah. So that is the thing right for now. That magnetic dipole moment is in inside. Okay? That is the thing. Okay. Now what can actually happen? You know, its condition is like, okay, I'll be saying this is X plane, Y plane, this is X plane, and this is coming outside is Z. That's what we are going to take as a convention for. Now, what we are going to do is assume there is a magnetic field in this direction from here to here. This is the direction of a magnetic field we are keeping. How this is kept? This might be kept due to some bar method you must be placing, right? This is north side, that will be sensor, this is south side. So this kind of magnetic field you are going to do. Okay. So how moving coil galvanometer is going to work? Let's see. So what magnetic this actually does is it detects your current, right? Detects your current. How it detects, we will see. Actually, I should have made it a little bit down, sorry. Just a second, I'll make it in second. Pictures. Yeah. Here I had a magnetic coil. Not magnetic coil, it's just a copper coil or something. Okay? Magnetic moment inside of it. Value I have already written over there. And this is kind of thing. Okay. This point, the top point is attached to a spring. What kind of thing? It is connected with a spring. So okay, what it is doing, basically when this thing gets rotates, it will take back to its position. This is connected with the top. Same at the bottom also. This thing is connected with the top, bottom. This is connected with the spring, spring. Okay, right? Basically, because look, when this gets rotated, this spring will get stretched in the circular format, right? So when you leave the external force or something, it will again come back to its initial position in a circular format. Okay, so this is what spring is going to do. Now we will see how this is going to help, right? So look here now in a normal spring when we talk about in normal spring, there's something called Q, right? What is that Q? Like this thing, right? The ratio. If you take it to stretch it. In case of circular spring like this, there's something called uh, torsional constant, okay? Torsional constant. Constant. Because here you are not applying force, here you are applying some torque to maintain it, right? Because when you want to rotate something, you need to apply some torque. Here if you want to rotate it, you need to apply some torque. That is what the torsion function will look like. Clear? What does this mean? It means if you wanted to rotate this spring by some angle theta, you need to apply what force equals to c times of theta. This is torsional constant. Understood? In cases of force, actually this should be torque. Okay? In this case, if you want to stretch it a little bit, you need to apply F is equal to force is equal to k distance x. This is spring constant. Here we have torsional constant. In case of spiral spring, okay? Spiral spring, this is also spiral spring. So this kind of thing is there. Now, if I ask you you are going to detect, how you are going to detect current. So I just told you, in general, this is connected, this galvanometer is going to connect it in a normal circuit. Right? Assume this is a normal circuit. Here you have kept a galvanometer and something like this, right? Makes sense. So galvanometers make something like that. There's a bar magnet or some magnetic thing is there. Okay. Assume magnetic field is like this. Because magnetic field is like this, B is like this. Can you see one thing? In this particular plane, if I talk about magnetic moment is pointing minus of right now in this as per this picture. Magnetic moment is in this direction, negative of k direction. B is in which direction? I direction, right? So you know when you keep this kind of thing in a circuit, assume this you have kept this thing in a circuit and there's a current on it. The moment there's a current flow, there will be some magnetic moment. Magnetic moment is there, magnetic field is there. You know what is the torque? Torque is nothing but M cross B. It means torque on this loop will be there, right? Now, how we detect current? When you provided some current, if there's a deflection, how deflection is there? It is rotated. Assume you keep up at the very top, you are keeping a pointer, okay, like this. So when this rotates, this pointer also rotates, and you say, "Sir, I am able to detect the current." Okay, this is one thing. The moment current you reduce the current, what will happen? Because of this spring, because look, whenever you are rotating, when it starts getting rotating, assume this is the earlier condition. Okay? When you rotate it, when this thing gets rotated, it will get compressed like this, tight, completely tight. Okay. When you release it, it will try to come back to its position, right? So this is what it is going to happen. Okay. So in this case, if you see in the current phase, I is in this. They both are perpendicular to each other, right? K and this direction. So is it the case? Is it that okay? Wait. Is it the case that this coil will always be 90 degree? May or may not be. Assume that I'm providing some current, and by anyhow this whole thing gets turned up in this case. Like earlier, it was like this. Okay, I supplied to some amount of current in this case, and what happened due to that current, this coil turned and get shifted in this position. Okay, now my magnetic field is passing this way. My magnetic moment is also this way. If now I calculate the torque on this, torque is zero. It means from here it is not going to rotate, and I have kept my current constant. Okay, makes sense. Now my current is constant. Now what I did, Kirtana, I increase some value of current. The moment I increase the value of current, will it going to increase? Will it going to rotate? No. Why? Because torque will come out as M cross P. What is the M? M is nothing but yes. This will become MB sine theta. Sine theta is zero. Zero. This will zero. Wait. It means from this position it is never going to rotate. Yes, if you remove the current. Why? Because in that case there won't be any force. Okay. In this case also, this torque from the top, this torsional torque is trying to rotate it back to its position, earlier position. But the moment it does it, you get some angle, and that angle again makes a torque field. So this is a balanced position, right? So how you are going to get to do that? This condition is also correct. Okay, this can also work. But if you see carefully, to work this case, this theta, this should also be always be making 90 degree or at least greater than 0 degree. Right? For this, what if I suggest you one idea that, sir, let's do one thing. Instead of having one plane, let's keep two planes. What does this mean? I have this kind of situation, okay, and I have another plane associated with this, and both will be having like sorry, it will be like this, okay. Now what will happen whenever this plane gets like this? For example, now magnetic field is in this way. You can see this plane, magnetic moment of this plane is parallel to this, but magnetic moment of this plane is perpendicular. Now this will help to rotate, okay, and this will help us to rotate. This will also. But the problem is, what if they get into situation like magnetic moment of both becomes 90 degree to 45 degree to each other. So in that case, what will happen? Look, at 90 degree, the torque is maximum, right? You will get torque maximum. But the problem is, it will always not be 90 degree with both of the planes. Okay, then what we can do? Let's apply one more plane. This is third plane already. Okay, still there's some chance. So what we did in real life when scenario when you see the coil is wounded in the complete circle. You have a circular coil. Okay, circular coil. In this case, we keep a circular magnetic field like this, magnetic field like this, magnetic field like this, magnetic field like this, a circular magnet. Okay. Now, if you talk about this plane, let's say magnetic field is in this way. Because now I'm not just saying that magnet is straight. Magnet is also circular. Okay. When magnet is also circular, in this case, assume this plane is perpendicular, right? Because it has a lot of you are basically you have wounded the wires like this. All the terms. Okay. So you have one length wire this side also, you have one length wire length this side also. Okay. So this okay, sorry. This wire here also this here also. So this particular magnetic field is perpendicular to this. Okay, this part of magnetic field is perpendicular to this. This part of magnetic field is perpendicular to that one. Okay, that one, this one. So this convention made it easier to use, or it will always ensure that there will be at least one loop in this which will be 90 degree to at least one portion of magnetic field. So Kirtana, is this concept clear to you? Moving coil galvanometer part.
Yes.
Okay. So in general, how we make it like this? If from the top view, you will see this kind of thing. Okay. There is a magnet inside. There's a coil inside. Okay. So it this kind of thing you can see from top. Okay. Now assume I'm just changing it to the circular part instead of just calling it as a square. Okay. Now this is a coil. And assume there is a coil. And here also, let's not make the magnetic, call it south, call it north. Okay, this kind of thing we are going to get. From top view, this will look like this. Okay, so what is the torque here? Torque is nothing but M cross B. But if I ask you, will it always be this thing? No, the reason is, if you see carefully, I just when I give you an example that I have one, right, then I have another coil, then I had third coil. So basically, a single galvanometer does not only contain one coil, right? Each have at least one M and one B, which is perpendicular to each other. Each have I also. So you can simply say, sir, in my galvanometer, there will be N coils. It means the same thing will be happening N times, right? So net torque will actually come out as look, so far whatever the coil and thing we have discussed, we were only discussing about single turn, right? What if they contain more turn? You can simply multiply that number of turns. So here also net torque comes out as N times of M cross basically magnetic field. What is the net magnetic moment? You can call that as NIA times of B, which comes out as NIAB. Okay, this is sine theta. Understood? Now we generally saying that Kirtana, initially everything was same, right? Initially everyone was perpendicular to at least one thing. So you can say that is zero. But what if I say when you provided say this torque, it moved by some angle, more some different angle theta, right? At initial condition, this initially for every coil the theta was 90 degree. So you can say that net max torque. This is the maximum value for torque. Okay, this is the maximum value for torque. Clear, Kirtana?
Yes, sir.
Okay. So from top view, assume this is a plane of wire where I can show you. Yeah, I'll try to make it over for you. This is a circle, bigger circle. Okay. This is a top view, and this kind of coil is there. The same actually, whatever I made there, I'm making here. Assume due to this magnetic field was like this. This is south, north. This was south. So in this particular, this is the center, right? Assume that when this thing rotated, this point moved by some angle theta to here. Okay. How much it get rotates by some angle theta. Makes sense. So in that case, now we have to calculate. Okay, assume that after moving to theta, because look, when you are trying to rotate it, if there is no torsion, it means it will start rotating. But I don't need a rotating motor. I need a galvanometer, right? So for this, we have kept a torque. If I'm saying after this angle theta, this stopped, can I say that here, whatever the torque you are providing, how much you provided this much? Can I say this torque T net is equals to torsional constant T spring? Can I say this? You can say this torque is coming up due to the magnetic field and this torque is coming due to the torsional constant. Is that clear, Kirtana? Let me know if you are clear with this thing or not.
Yes, sir.
Clear, right? Okay. So I just told you, we have just gone through this. This spring torque is nothing but equals to torque magnetic field. What is the value of magnetic field? That is I, A, P, right, and N, total number of turns. And also this torsional constant, I told you, this is directly proportional to its constant and how much angle it has rotated. So you can simply say, so this is equals to k times of theta. Let's call the spring constant is k. Okay. Torsional constant, the spring constant is k is equals to I a b times of n. This is the value. So a b n. So how much angle you have rotated, that is going to be equals to I a b n by k. It means if I gave you some current value a, if I gave you some current, rest of the things are given, and I ask you how much this galvanometer coil is going to rotate. This is that theta. Okay. That is how you are going to detect current. How you are going to detect? Assume that I have made a device. Okay. Assume the whole coil is here. So when this is the pinpoint which is going to rotate. Initial condition when there is no current, this pinpoint is pointing like this. The moment if you provided some current, this gets rotated by some angle theta. Maybe let's say it reached here. Okay. So what we are going to do is for this angle theta, maybe let's say you are saying this is zero, here it is angle some theta. So you will be mapping from zero to theta. What you are going to map, you are going to map, sir, for what current I am at zero and for what current I am at theta. So I assume I am saying that when you have a current 10 degree, you are at 0 degree angle. When the current is 100 degree, you are at maybe 50 degree angle. Okay. So your yeah, what's the difference? Let's say initially zero angle, 0 ampere at the zero. So you can simply say, sir, for 100 degree moment, I need current difference of how much? 50. It means if I provide 1 ampere of current, sorry, what I provide? Yeah, this is ampere, right? Wait. For 1 ampere of current, okay, for 100 ampere of current, it is going to rotate by 50. It means to say if you provide 1 ampere of current, this is going to rotate by 1 by 2 degree. Is that clear? So that's how we generally make this kind of instrument. Clear, Preetham?
Yes, sir.
Okay. Any doubt? No doubt, right?
No doubt.
Okay. Okay. So that's how actually we make this thing. Okay. Let's move to the next page and let's talk about magnetic moment. So Kirtan, we already know that magnetic moment is nothing but just a second. Yeah, magnetic moment. If I ask you what is the magnetic moment, is for now so far you must have be clear that magnetic moment is nothing but I multiplied by current multiplied by this. These two things will gives you, right? If you have n number of terms, then this is the answer. But what if I give you this kind of scenario? Just think of it once. This is your y-axis, okay? This is your x-axis. Be careful with this, and this is going to be your z-axis, okay? Just look at this. Now I am saying, in this case, I am having a wire. What kind of wire? This wire is kept. This part is in xy plane, okay? There's a current in this way. The same. Now this portion is kept on YZ plane. This is Y, right? Sorry. This is Y, this is Z. So, and these 2 points are connected. So you can say this portion is lying in YZ plane. Yeah, this portion is lying in YZ plane. This is lying in X and Y plane, and this is lying in X and Z plane. Okay. And current is again because current is same constant, right? So it will be like this, then this and this because all of them are connected. This is a single wire. Basically, you had three axes. Okay, you can say this is one wall. This is adjacent wall like this. Okay, okay, I'll just make it in a wall format so it might be suitable for you. This is one wall. Okay, then at 90 degree you had another wall like this. Okay, and this was the ground. This is the ground for you. So what you did, you kept a light. You made a small square at this part, okay? Then on the other side of wall you made it like this, and then in bottom from ground you join both of them. Put it. This kind of thing happened to you. Understood? I hope this is clear to you now. Mm, this. Okay, this kind of scenario is given. So I'm saying the current is I itself. Okay, current, the value of current is given is I itself. I I itself. Okay, here you can see the current is I. So can you calculate magnetic moment, magnetic dipole moment? Here, if I ask you, find magnetic dipole moment. Krishna, if you want, give a try to this. Find magnetic dipole moment. Look, the problem here is it is not even complete part like this on this, so that you can say for this is this side, for this side, for bottom it is upside, and I can take vector addition of this. No, because this is just a single wire, right, which is spread on all these things. This, you can't even take direct angle of this also. So Krita, just look at this, how you are going to solve it. Any idea, Krita, how you can try to solve this one?
No, sir.
Look, Krita, whenever you get this kind of problem, go with some imagination. What is that? Let's see. If I say Krita, in this part, do I have any angle? Do I have any current? What if I say Krita, here I am imagining a current? You will just say how you are imagining a current. In this way, we don't have any current. Okay, makes sense. I am imagining an opposite current also. Yeah, now I can say this is I, here it is minus I, the net is 0. Yes, in this Y, I don't have any current. Can I do here also? Yes. I upside, I downside. Okay, makes sense. Here also 0 current. What about this? Let's do here also. I this side, I this side. Wait, what I got is at the bottom I got this situation like this at this plane. I have got this kind of situation. Current is going in this way. No, sorry. This. Okay, it should be actually this way. So current is going actually this way, and this plane I'm getting like this kind of condition. Clear? Understood it, Kirtana?
Yes,
Can you do here? Because you know the separate of this. What is that? Area you know, current you know, right? Complete area. You will say, sir, the angle, the magnetic field due to this plane is coming in this plane, right? Because here you are in x and y plane, right? So magnetic field due to this will come in into directly z plane because here this z plane. Sorry, this will give you in z plane. What about this bottom part? This will give you in y plane. This will give you in what is that plane? This x plane. Okay. So you can say you will be having three vectors like this: magnetic moment in mx plus my plus mz. You just need to add all of them. Okay. This is what you need to do in this case. Clear?
yes, sir.
This will be this will be m net. Okay, are you really clear with this thing or not? Right.
Yes,
It's clear, right? Okay, I'm not just putting the values. Uh, okay, now that's fine, Kirtan. Now what I'm saying is, let's take another thing that you are given a circular disc. Okay, this is a disc given to you. Okay, it will make a disc. Yeah, this is a disc. Okay, have some radius on it. At this point, there's a axis coming out. About this axis, what I did, I rotated it by angular frequency omega, angular velocity you can say. In if you look at, okay, this is top view, Side view will look like side view. I'll just make side view for this. It is like this. This it is rotating with some omega. This is the thing. It's a disk. It's a disk. Okay. Now what I did is there's a magnetic field upside inside. What does this mean? Magnetic field inside in the whole region. Okay. Magnetic field is inside the B. So in this particular case, Kirtana, your task is to find magnetic moment. Magnetic moment. Look, earlier cases you simply went and calculated like what you did in the previous cases. Simply said, sir, I is the current, area is the area. Its area is like this. So the magnetic moment will come out like this. I will, right? But how you are going to calculate in this particular case? I can easily this problem for you. Let's say instead of saying this to be a disk, I'm calling it a ring. Because when I'm calling it as a ring only contains mass at the outside. Right? I'm calling this as a ring, and the ring only contains mass at the outside. Now can you solve this problem? Can you calculate the value of magnetic moment?
Always.
Try it once and let me know the answer. Try it once, okay? I have decreased some load on you by calling it just a ring instead of calling it as a disk. Because you know, in case of this, sometimes we have to take internal angles. We have to say this is a small portion, then integrate it from internal to outside. So this thing makes it difficult. So it's better to calculate disk ring first, then we can actually go to the disk also in future if we want it. So yeah, we can just go once and let me the answer first. Take 3 minutes, not more than that. Okay. I'm calculating. Let me know the answer. Kirtana, I will give you a hint that in these kind of problems, whenever see, always try to look about electrons, rotating electrons inside.
Sir, can you explain it?
All right. So the here part is we actually do is yeah. Now look, so let's take a top view first. What I said, Kirtana, that okay, this kind of circle you have, right? When I said this is rotating about this, okay, and I said there is a magnetic field downside. Makes sense. Yeah, it is. Uh, how this is actually happening? If can I say that it is rotating? What does this mean? This is nothing but made up of electrons inside. So can I say there's an electron at this point, there are electrons at this point, electrons at this point? Yes, it is. It is rotating by some angle. What is that? Okay. Kirtana, that is fine. I am asking you one thing. There's a circle. Okay. Basically, there's a particle over here at this point. If he is rotating in the circle with velocity omega, this radius is r. Can you tell me his velocity in this direction? Can you compute the value of velocity in this direction? Kirtana, are you there? I'm asking what is the velocity of that in that direction? Yeah, Kirtana, just let me know the velocity of the particle. I'll explain the rest of the part.
Omega.
All right, so if the velocity is omega r, what will be the velocity of electrons? Any single electron you can tell me. Because it's conducting, non-conducting thing, okay? It is non-conducting all I forget to. This is non-conducting, so it means electrons are sitting at the point, right? It is rotating, it means each electron has the same velocity. What is that velocity? If this radius is r, this is omega. So what is the velocity each of them has gone? Omega times, right? Can say this? Yes, it can. Now the thing looks like that. In this circle, your electrons are moving in this loop, right? This electron is here moving in this direction, electron is here moving. Can I say it is looking like if electrons are moving in this whole direction, what is the current? Current is always opposite, right? Okay, makes sense. So what is the electron? Like what is the number of electron? I can simply say whatever the charge on this. So you can simply say the current on it will be nothing but what is the current on this? Just a second, let me remove it. Yeah, current will be nothing but charge divided by the time, right? Makes sense. What is the time? I don't know time. Time I know just one thing omega. What is omega? Omega suggests that change in theta divided by time, right? What does this mean? How much revolution, like how much angle you are going to rotate in how much time. So you know in complete 2 pi, the time is t. Okay. So what is time period? 2 pi by omega. Okay. I can say that in one revolution, what is the current? Current is nothing but Q divided by this T. Understood? Because assume I don't know anything, all electrons are sitting. At this point, this rotation started. So when all these electrons, like these number of electrons, will complete turn back, can I say in this t time, all electrons have passed through this? Yes, all of them have passed through this. Okay, so this current comes out as Q by T. Okay, what is that? I now this comes out as Q divided by 2 pi by omega. This is current level. Make sense? Now, what was the main task to calculate? The main task was magnetic moment. What is magnetic moment? I into E. Clear case now? Now, what is magnetic moment? Current Q omega by 2 pi into A area. Yeah, Kirtana, is it clear? Understood?
Yes.
Any doubt?
Yes.
No doubt, right? Okay. Okay. If I put the value over here for now, if I just keep the value instead, let's see what is the area we have asked. It. What is the area? Omega pi r square divided by 2. Pi is cancelled. So m comes out as q omega r square divided by 2. Right? So this is what you are going to do. Understood? Okay, so Ketna, I'll explain you one more thing. If I divide this magnetic dipole moment m whatever value by angular moment, can you tell me the angular momentum value of angular momentum of this situation? If it has a mass m, assume this ring has mass m. Can you tell me the angular momentum? Tell me the angular momentum. Kirtana, what's the angular momentum of this situation? Whatever.
Q omega square by 2.
Alright, Krishna. So you can simply just put the values q omega r square divided by 2. Whole thing if you divide with angular momentum. What is angular momentum? M, M, omega
And
r, right? Omega r, can I keep? Omega r square. Okay? This is the angular momentum. So this will give you cancel. What is that? Q by 2. Right? This is generally uh, the ratio of dipole moment of electron to angular moment of electron. This gives you the value. Okay, in general. So, Kirtana, yes, do you have any doubt in this case? Kirtana, do you have any doubt? No doubt, right? Okay. Let's talk about one more problem. This is a point, pivotal point. About this, there's a rod. Okay. It is rotating with some angular velocity omega. Okay. This is a rod, just a rod. You need to calculate. Yeah, this rod has a charge Q, mass M, and length L. You need to calculate. Uh, One more thing. This is rotating uniformly, so you need to calculate. Find magnetic moment, magnetic dipole moment. That's what you need to calculate. Now. So just let me know the value for this. Kirtan, you can just calculate this and let me know first. Kirtan, solve this once and let me know. Okay, this last problem
The
for today's session. Well,
M-
yeah, what happened? Have you got the answer?
ML into Q omega beta.
I can just hear that ML into something. Although the answer will not be in the part of ML itself. Okay, Kirtana, I'll just give you the ones. Look, just previous section which we have studied, I can actually go with that magnetic moment of something divided by angular moment of this thing will result you how much? Total charge divided by total mass, right? Okay. Can I directly calculate angular momentum? Yes. What is that angular momentum? Can I get to know the value of angular momentum? Yes. Q by 2. Angular momentum of a rotated body is nothing but if it's a rod, right? In general, what is angular momentum? Angular momentum is nothing but mass into inertia into omega. Right? What is inertia in this case? You can see you are rotating a rod about with this axis, right? What is the value in that case? M L is Q divided by the 3. Okay, sorry, it should be ml square divided by 3 into omega. So just put this value ml square into 5. You get the answer, mm get cancelled out. Q m. This is one answer. This is one way to calculate it. Okay. Just remember, if you remember this thing, you can directly get this value. Otherwise, if you don't know, again, I have another method also. What is that? If I say when this rod is rotating, can I say that there's an electron over here, right? Which is, assume I'm just sticking to this point, and there's an electron which is rotating around the circle. From top view, how you are going to see this rod is rotating around, right? If you just focus on this electron, how this is rotating like this. A rotating electron can act as a current. Right? If it acts as a current, we can actually calculate the value. Right? How you are going to calculate that? Let's see. We know that you just do one thing, go at some distance x, take out small element dx. Okay, so you know the mass of this dx, right? Tm is equals to m total mass divided by total length L times of dx. This is the small. Okay, it's a very small concept of density part from where you can get. So if I ask you angular momentum due to this, like magnetic moment due to this single electron part, what is that? Whatever the current it is creating, whatever the area it is taking, how much area it is taking, something pi x square. This is the area it is making, right? Because it is at some distance x, so it can only make a circle of pi x square. So magnetic moment that due to that will be nothing but current I. What is that I? You know that is charge, that is dq divided by time. One revolution, because it's omega, it will always be 2 omega by pi. So this is whole the current comes out multiplied by what is that? Sorry, multiplied by area. What is that? Pi r square x square. We have just solved the whole thing also. What is that? Q omega r square by 2. This is the magnetic moment comes out, right? So here also this thing comes out directly as dq omega as it is, instead of r keep x square divided by 2. This is the value you are getting. You can actually do one thing. You can just integrate this how from here. But wait, here you have this also variable, this also. What is charge? Total charge is q. So this dq can be represented in the form of q by l dq. Okay, sorry, uh, dx. Actually. This is what you can actually put. So instead of dq, you can put this. When you do this, you are going to get q by l omega x square, dx is there, and there's a 2. Just integrate this. The moment you integrate this, you are going to get the answer. Okay? Is it clear, Kirtana, this concept so far?
Yes.
It's clear, right? Okay, any doubt? Okay, so yeah, sorry, there's an L. So when you integrate it, I'll just give you the complete value 2L omega integrated to x cube by 3. From where to where you have going? You are going from 0 to complete an L, so this becomes L to L. Q omega, this x cube, instead L cube divided by 2L. This becomes 6, 2 into 2. So you have got Q omega L square divided by 6. Isn't it the same way? The way is same. You can see just one line, another line. Answer. Here you need to do a complete integration, keeping track of each of the angle, small element, whatever you have taken. So just see what's the difference. Right? If you have any doubt, please let me know. Otherwise, we can end the session. I will still. Yeah, right. Okay. So yeah, Kirtana, that's all for the today's session. Look, Kirtana, we are about to end this chapter, so I will suggest you please revise the complete chapter once again. If you have doubt, I'm ready to take one more session for you, where I can clarify all your doubt in a complete physics. Okay, so whenever you want a doubt session, you can tell to them. That will be specific to the doubt session. See you again. Goodbye. I'm in the